Everyone, good afternoon and thank you for attending this talk. My name is Sarah Masood. I'm an assistant professor of industrial and systems engineering at Maine State University. Today, I will be presenting my work titled A Sensor-Based Data-Driven Framework to Investigate PM2.5 in the Greater Detroit Area. Let us start by having a quick look over the outline of this talk. The talk starts with a short introduction on some of the key definitions. Then I continue to talk about what motivated us and the problem statement. Then I will cover our proposed framework and provide a quick look at the long short-term memory models and dynamic time warping, which are the key components of our proposed framework. Finally, I will illustrate the experimental setting and go over the result, our findings, conclusion, and the future works. PM2.5 refers to atmospheric particulate matter in solid or liquid form that have a diameter less than 2.5 micrometers, which as shown in the provided figure is about 3% the diameter of a human hair. Given their small size, fine particles tend to stay longer in the air, which increases the chances of humans or animals inhaling them. Owing to their minute size, particles smaller than 2.5 micrometers are able to bypass the nose and throat and penetrate deep in the lungs, and some may even enter the circulatory system. Many adverse health effects have been linked to particulate matter, such as premature death, lung disease, development of chronic lung diseases, heart attacks, respiratory symptoms, decreased lung functionalities, and preterm birth. As a result, Air Quality Index, or AQI in short, is defined by government agencies to communicate to the public how polluted the air currently is or how polluted it is forecast to become. Public health risk increases as the AQI rises. Particles can come from various sources such as power plants, motor vehicles, airplanes, residential wood burning, forest fires, agricultural burning, volcano eruptions, and dust storms. These sources are categorized into four main groups. First, mobile sources such as vehicles. Second, stationary sources such as power plants and factories. Third, natural sources such as forest fires and volcanoes. And finally, area sources such as dry cleaners and gas stations. The United States Environmental Protection Agency, or EPA in short, has enacted a set of strict standards to monitor and control PM2.5. Using a nationwide network of monitoring sites, EPA has developed ambient air quality. Under the Clean Air Act, EPA sets and reviews national air quality standards for particulate matter. Air quality monitors measure concentrations of PM throughout the country. EPA, state, tribal, and local agencies use that data to ensure that PM in the air is at a level that protects public health and the environment. There are many instances in the literature that demonstrates how meteorological conditions can largely diffuse, dilute, and accumulate pollutants. Thus, PM2.5 mass concentrations can be mainly affected due to meteorological conditions. As air movements influences the fate of air pollutants, any study of air pollution should include a study of the local weather patterns, wind, temperature, humidity, pressure, dew, and weather conditions. It has been shown that meteorological conditions can at least make a contribution of 16% to the reduction of PM2.5 mass concentrations. Analyzing the spatial distribution of PM2.5 concentrations, as well as their spatial differences, is believed to benefit the study of spatiotemporal variation of air pollution and provided scientific references to the control of air pollution. Our proposed framework is built upon two major sections: data acquisition and data analysis. The data acquisition process starts by automated web scraping, the process of extracting data from websites automatically, where our proposed framework reads the current PM2.5 values, humidity, temperature, and pressure data of 15 different air quality sensors within the greater Detroit area at a rate of 3 readings per hour. Air quality sensors' real-time data are downloaded in a JSON format. This step further processes the data to format them into a desired structure and estimates missing values if possible. In the next step, data association, the readings from different locations and weather condition data are associated through their timestamps. The final step covers the outlier detection via a sliding window prediction approach. During the data acquisition section, the locations suffering from severe missing values are dropped. The next section of our proposed framework is data analysis, which covers temporal analysis of impact of meteorological factors on PM2.5 concentrations, and a spatiotemporal analysis of PM2.5 concentrations over time at different locations within the greater Detroit area, using long short-term memory and dynamic time warping methods respectively. Utilized air quality sensors in this study are PA2, or the second version of PurpleAir sensors, that measure real-time PM2.5 concentrations. The built-in Wi-Fi feature enables the sensors to transmit data to the PurpleAir map, as shown in the right, where it's stored and made available to any smart devices. In addition to PM2.5, these sensors are capable of measuring pressure in millibars, percentage humidity, and temperature in Fahrenheit. Every icon on the PurpleAir map represents a public PurpleAir sensors, and the color indicates the real-time PM2.5 readings on the EPA Air Quality Index scale. Recurrent neural network, or RNN in short, is a generalization of feed-forward neural network that has an internal memory. RNN is recurrent in nature as it performs the same function for every input of data, while the output of the current input depends on the past one computation. Networks have the form of a chain of repeating modules of neural networks. In the standard RNNs, this repeating module will have a very simple structure, such as a single TAND layer. Long short-term memory models, in short LSTMs, are a specific form of RNNs that were introduced at 1997. LSTMs work tremendously well on a large variety of problems and are now widely used. LSTMs are explicitly designed to avoid the long-term dependency problems of RNNs, as remembering information for long periods of time is particularly their default behavior. The gating functions that make up the LSTM networks are the input gate, the output gate, and the forget gate. The input gate protects the contents of the memory cell from the disturbance of any unwanted inputs, while the output gate protects their units from those same unwanted inputs. These gates manage the flow of information through the cell and neural network by utilizing tan and sigmoid functions. Sigmoid function, shown on the right, outputs any given input into a number between 0 and 1. It is used as a gating function for the forget, input, and output gates in LSTMs, as it can block and or allow flow of the information throughout the gates. Although sigmoid function performs perfectly for managing flow for the forget, input, and output gates, it is suffering from the vanishing gradient problem. As shown in the right, the derivative of sigmoid function grow into very small value as inputs values go too high or too low. To overcome this problem, tan function, whose second derivative can sustain over a long range, is implemented in LSTM networks, as displayed on the left. Using the sigmoid and tan functions, the gates and their associated operations in an LSTM cell are defined. The forget gate applies the sigmoid function on the previous hidden state and current input to decide what information should be forgotten. The next two equations model the input gate by outputting the information to be updated through applying a sigmoid function on the previous hidden state and current input, and creating candidate values by applying a tan function on the previous hidden state and current input. The next equation updates the cell state by forgetting what should be forgotten from the previous state and adding the new information to be updated. The next equation models outgoing output through the output layer by applying a sigmoid function on the previous hidden state and current inputs. Lastly, the hidden layer gets updated through applying a tan function on the current cell state multiplied by the output layer's outcomes. In designing an LSTM model, 8 weight parameters and 4 biases are implemented, which are associated with inputs and previous hidden states as displayed in the figure. The weight parameters are designed to control the signal strength between neurons. On the other hand, biases, although connected to the input weight parameters, are offset additional inputs that are independent from the previous layer. Both biases and weight play a significant role in optimizing the LSTM model. In time series analysis, dynamic time warping is one of the major algorithms for measuring similarities between two temporal sequences. Euclidean matching, although a very well-known alternative, produces a poor similarity score as it aligns the ith point on the first time series with the exact ith point on the second one. On the other hand, dynamic time warping matching produces a more intuitive similarity measure due to its nonlinearity nature, allowing similar shapes to match even if they are out of phase in the time axis. Restrictions on the warping function include monotonicity, continuity, boundary conditions, warping window, and shape constraint. The algorithm behind dynamic time warping is really simple. It means that the cost of between two sequences with length I and j equals the distance between the tail plus the minimum of cost in arrays with length I minus 1 and j, I and j minus 1, and I minus 1 and j minus 1. Finding the optimal alignment can be quite slow because it requires comparing each element of the first time series, for example Q, with each element of the second one, for example S. Furthermore, it can lead to bad alignment where a relatively small part of the one time series is mapped onto a large section of the other one. This can be avoided by narrowing the searching window around the diagonal of the warping matrix using global constraint. On the right side, you can see the two most frequently used global constraints, the Sakuchiba band and the Itakura parallelogram. When it comes to the Sakuchiba band, it has been shown that apart from speeding up the computation process, the constraint dynamic time warping qualitatively differs from the unconstrained one and has shown improved accuracy. The Itakura constraint region is a parallelogram. Contrary to Sakuchiba band, whose width is constant, the Itakura parallelogram has a varying width allowing for larger time shift in middle than at the first or the last points. It has also been shown that Itakura parallelogram not only further reduces the cost in terms of computation in comparison with Sakuchiba, but also produces lower error rates when it's compared with Sakuchiba band. For the experiment, we gathered PM2.5 readings in addition to humidity, temperature, and pressure data over all PurpleAir sensors placed in Greater Detroit area with a frequency of 3 reads per hour over 2 months in winter 2019. The relative wind and dew information as well as weather conditions were scrapped from open source weather APIs. Out of the 15 PurpleAir sensors placed in Detroit, only 6 of them continuously provided statistically significant data, and as a result, we dropped the remaining 9 locations for this study. Here you can see the plotted time series for the mentioned data. LSTM models have been developed for the 6 different locations, and all models are reporting low loss and RMSE values. The RMSE is the square root of the variance of the residuals. It indicates the absolute fit of the model to the data, or equivalently, how close the observed data points are to the model's predicted values. Low values of reported RMSE, less than 4 for all models, indicate the greatness of fit for the developed models. Here, dynamic time warping is used to measure pairwise spatiotemporal similarities between PM2.5 readings in different locations. The bottom left displays a 3-way PM2.5 time series alignment, while the top right displays cumulative distance density plot with symmetric steps and Itakura parallelogram window. A straight diagonal line in the 3-way PM2.5 time series alignments or a green area on the cumulative distance density plot displays or illustrates high similarity scores for the compared time series. There is only one location, location 6, which is showing diversion from other PM2.5 patterns. Further root cause analysis to find the reason behind these detected spatial anomalies are required. As for conclusion, we started by scraping data from 15 different PurpleAir sensors over the greater Detroit area. We trained exogenous LSTM models to predict PM2.5 concentrations based on meteorological features, weather conditions, and PM2.5 concentrations over a 24-hour time frame. We utilized dynamic time warping with Itakura parallelogram window constraints to compare the spatiotemporal patterns of PM2.5 concentrations over the greater Detroit area. For the future work, we will be calibrating these PurpleAir PM2.5 readings based on EPA ground stations, and we will be performing root cause analysis to find the reason behind detected spatial anomaly. That's all for today, and by that I'm concluding my presentation, and I would be happy to answer your questions.